Hi, this is the first video of Applied Microeconometrics. My name is Eik van Vuren. I'm a professor in econometrics here at the University of Groningen. I started about 2 years ago, and well, before that time, I was a university professor at the University of Gothenburg in Sweden, and also there I was a professor in econometrics. That is about me. A little bit more about the things I'm going to say during this lecture series. And as it actually says here, I'm going to talk about quantile and distribution regressions. Well, this video will mainly be an introduction, well, essentially about the motivation of why we are going to look at quantile and distribution regressions. These are topics that are relatively new. I say relatively new because of the fact that we should realize that quantile regression analysis is already, well, 40 to 45 years old. So that doesn't sound for a lot of you very new. But we should take into account that if you compare it to standard regression, well, standard regression analysis already exists for more than 100 years. So in that sense, it is actually the case that quantile regression is relatively new. Distribution regression is much newer. That exists since around the turn of the century, so 20 to 25 years. But we should also take into account, like with many other topics in econometrics, that even though they were maybe discovered already a long time ago, well, they are still developed. And that is the topic of, well, my part of the lecture series in Applied Microeconometrics. But as I said, today I'm not going to talk too much about quantile and distribution regression itself. I'm more looking at an introduction and motivation for why we would like to do quantile and distribution regression analysis. Before I'm going to do that, I would like to say something about the individual and the group assignment. Well, I know that I make myself very popular by looking at the individual and group assignment already at the start, but I do think it's interesting to do it in this way this year. And the individual and group assignment this year is going to be based on a data set from the ILO, the International Labour Organization. I suppose that you have already heard about that particular organization. Probably not about the data set. I'm going to talk about that on the next slide. However, at least for the individual assignment, I also allow you to work with respect to your own data set. Then the group assignment. Well, I will post the group assignment already this week, but what I will do is that, well, the group assignment will actually be either quantile or distribution regression based on a country preference. What that actually means, you will see that at the next couple of slides because of the fact that that's actually related to the data set from the ILO. Then the individual assignment, well, that will be a very short essay of about 3 pages. Well, you could write it up to 4 pages maximum. And these are the restrictions with respect to this. It's going to be essentially not really a paper, but the idea is that you're just going to do a very short empirical exercise with respect to the things that we have been talking about. The individual assignment can be about anything. Well, not really anything. It has to deal with the things that I actually have been talking about during this lecture series. But it can be, well, about anything related to the lecture series. It's not restricted to a particular kind of topic. And, well, you could use this data set that we have over here, but you can also use your own data sets, including, for example, data sets that you are using for your master thesis. And then finally, you could even do simulations at the moment that you would like to look at that as well. It's allowed to work together. So even though I call this an individual assignment, it's allowed to work together. You still have to, of course, hand it in individually, but you are allowed to work together. You have to, of course, say that. And it is going to be in groups of 2. Then at that moment in time, I expect you to write a paper, which is a little bit longer, of course, if you work together, about, say, 6 5, 6, 7 pages maximum. And another thing that I'm asking you to do at the moment that you work together is that you at least are going to provide in, say, an additional very short file what you have been doing. So whose idea was, who was done the empirical exercises, who was written everything down and things like that. It is allowed to write there that you have done everything together, but it's also allowed to write down exactly who has done what. And well, the topic can be discussed in the second lecture of week 3. That's going to be my last lecture. Well, then a little bit more about the data set that we're going to use during our, say, assignments. That's called the School to Work Transition Survey. It's a survey of 23 developing and emerging economies for the year 2012. And the idea is that, as actually the name already indicates, it is going to look at young individuals that go from school towards work. So it's a household sample. However, even though it's a household sample, and that means, of course, that in principle, the individuals that live in that particular household could be quite old, there only those individuals between 15 and 20 years of age, they are going to be sampled in the household. So these are going to be in our data set. Well, there's data available on labor market status. So that's there's a lot of, well, data available there with respect to what individuals are actually doing, like working, self-employed, whether you're an unpaid family worker or whether you're studying. Not so strange, of course, because of the fact that these people are very young. So it's not that strange if they are still studying. But yeah, at least some of them, especially the older ones, they may already be working or they may be self-employed. Also data available on wages. And that's very important for our analysis because of the fact that we essentially are going to look at wages. But it's also possible, and that's very interesting with respect to this data set that we have over here, it's even possible to look at the profits in the case that individuals are self-employed. Take into account that these are self-reported wages and profits, so it's not something that comes directly from the tax office, but instead it's based on what people actually indicate to be their wages and the profits. We have demographic variables. First of all, we have the age of individuals. We also know whether individuals live in a rural or an urban area, and we have the gender. Well, actually we have a lot more detailed variables, as well as that we have the education levels of the individuals. Well, then the countries that we have, as I already said, we have 23 developing and emerging economies. Well, they're actually spread around the whole world. We have Eastern Europe, Southeast Asia, Latin America, Africa, and the Arab states. Well, most of these countries are quite well known, of course, especially if you think about Russia. But, well, there are also some of them that I at least do not know that much about, Kyrgyzstan. Well, to make things complete, here actually are the different countries, as I already said. I'm pretty sure that most of these countries are well known to you. I suppose that Kyrgyzstan is somewhere over here. Well, these are all the countries that you can actually look at. Well, that was then the group and the individual assignment, or at least a description of what you have to do during the individual and the group assignment. And that, that means that I now come to the real introduction with respect to the things that we would like to do today. Well, as I said, what we're going to do in the end is that we are going to look at quantile and distribution regression as an alternative to standard models. But in order to motivate it, why we actually need these kind of models, I would like to start with a very simple and well-known model that you have already seen many, many times before. And that's the linear regression model. Well, I'm sure that you have seen this equation before. We have at the left-hand side yi, and at the right hand side we have xi times beta plus ui. I'm going to make the standard assumptions over here. Well, the main assumption that you at least typically have to make it at the moment that you would like to estimate this with standard ordinary squares is that x and u, they should be uncorrelated with each other. But apart from that, you don't need that many additional assumptions apart, of course, from this model itself. Well, in order to make the introduction a little bit more, well, exciting, or at least to understand this a little bit better, it's always good to think about a particular application or a particular example. I'm a labor economist, and therefore I do think that it's interesting here to have wages at the left-hand side, or maybe better, log wages at the left-hand side. And at the right-hand side, you can think of a situation in which we have all kinds of human capital characteristics, including, of course, the education level of a particular individual, but all kinds of other characteristics that are going to have an impact on the wage of a particular individual, like, for example, well, the gender of the individual, the region of the individual, and the ethnic background of that particular individual. So these are all kinds of things that are going to be important in the end to explain the log wages. This is just an example, but that actually makes the example a little bit more easy to understand, or the framework that we have over here a little bit easier to understand. UI, well, UI is then everything that is still going to have an impact on the wages of individuals that we cannot actually not observe. Apart from the fact that there might be some luck here, some people just are very lucky to find a nice job and therefore have a higher wage, we can also think of things as talents of individuals. Some individuals have very good talents and therefore they have higher wages, and other individuals do not have that many talents and therefore their wages are going to be lower. So this is now going to be our model. We do already know that there are a lot of limitations with respect to this model. Well, apart from the fact that we generally have to assume that x and u are uncorrelated with each other, at the moment that we would like to estimate this with standard ordinary squares, another thing that you should realize is that the model itself already is an assumption as well. That means, of course, that we have this assumption here of linearity, but you should take into account that there's also another very important assumption that usually is, well, not made that clear during many econometrics classes. And that is that what we are going to assume here is that, of course, x has an impact on y. That's generally the case because of the fact that x is a right-hand side variable, so therefore x has an impact on y. But what we're going to assume by this equation that we have over here is that the impact that x has, any kind of x has, is exactly the same for every individual. To make this a little bit more clear, if we go back to the example that we looked at before, then at the moment that we have here log wages, and at the right hand side we could, for example, have whether somebody has a university degree or not. So one of the x's that we have over here is a dummy for having university education or not. Suppose that, as I said here, we have log wages. Well, then the beta coefficient is going to give us a percentage. So suppose that this thing is equal to 0.4. So that means that at the moment that you're going to have, well, university education, your wage is going to go up by exactly 40%. That's the interpretation, but the most important thing is that you should realize that that's actually true for everybody. So everybody is going to increase their wages by 40% at the moment that they are going to have a university degree compared to the situation in which they do not have a university degree. So an important assumption that we're going to make over here is that the returns to education are going to be exactly the same for everybody. Everybody gets exactly the same return for education. Well, that may not be true, of course. It may be possible that particular individuals have a higher return to education than other individuals. That may be related to their talents. It may be possible that they have particular kind of talents that make it that their returns to education at the moment that they have a university degree the wages are going to be increasing more than for other individuals that do not have those kind of talents. So therefore you should realize that this assumption that we actually make over here may not be correct. It may not be the case that all the individuals have exactly the same returns to education. And we should take into account that that's immediately problematic. This is problematic, as we will see later on, at the moment that we would like to do econometric research. But we should also take into account that this is problematic at the moment that we would like to do policy analysis. And the reason behind that is because of the fact that, well, suppose that at a particular moment in time, a policymaker would like to invest in education. So suppose that a policymaker would like to invest in education because of the fact that the policymaker has the idea that that will increase the productivity of the individual. It means that the wages will actually go up. And that's also good for the policymaker because of the fact that if wages are higher, then you can also raise more taxes. So suppose that really the policymaker would like to invest in education. Policymaker can do that, for example, by saying like, well, we are going to, well, first of all, improve the quality of universities. But they can also do that by making university education more attractive. They could, for example, lower the tuition fees. But they can also decide to, for example, increase, say, the scholarships of people that are going to go to university. Well, that implies, of course, that more individuals are going to go to university, and that implies that the wages of the individuals may actually go up. But the question arises, by how much? Well, what we do usually in econometrics is that we then are going to look at the individuals that already went to university and look actually how large their wages, how high their wages are in comparison to the situation in which they would not have gone to university. Well, that's of course possible. It would be maybe possible to look at a situation in which we are going to have the returns to education of the individuals that actually went to education, that went to university. But we should take into account that these are typically individuals that have the highest returns to education, the highest return to university, because of the fact that that's the reason why they actually chose to actually go for university, even in the case that it maybe was not that attractive yet to go to university. The moment that you make it more attractive to go to university, then more people will of course study and they will start university. But you should take into account that a lot of them will have a lower return to education than the people that you already have in, say, university right now. And that means that you're going to definitely overestimate, overassess the impact that your investments are going to have. So you should realize that this is actually important. So therefore, what we can do is that we could try to introduce a new kind of model. Well, for that we are going to look at this model that we have over here, and this is called the random coefficients model. The random coefficients model has on the left hand side again a yi, and the right hand side we have again an xi, and again we have a beta and the ui that we also had the previous slide. Well, that implies that you might get the idea that based on this, that this model that we have over here is almost identical to the model that we have on this slide, but that's actually not true. You should take into account that these two models may be as opposite from each other than you can actually have in econometrics. That's to say that in many lecture series that you get from econometrics, then, well, people are going to start maybe with this model over here, and then they're going to look at, say, extensions of the linear regression model. They're going to look at IV, and they're going to look at all kinds of other, well, maybe non-linear regression models. They might even try to look at extensions, further extensions with respect to that. But you should take into account that usually the steps are not that big. However, if we go from this slide to this slide that we have over here, now we have made a really huge step in econometrics. And the reason behind the fact that this model is quite different from the model that we had in the previous slide is because of the fact that you should realize that beta here is no longer really a coefficient as what we had over there, but it's now going to be a function. It's a function in this case of ui, of the unobserved component. And this allows for the fact that, say, the x's are going to have a different impact for different individuals, depending on the outcome of the ui that we have over here. Because of the fact that now ui directly has an impact on this beta that we have over here, and that was not the case over here. You should realize that this model is quite special in that respect, because of the fact that we do see that at the moment that we're going to change ui, then it is going to have, of course, an impact on yi, but it's actually not having any impact on how beta, or in fact xi, is going to change the yi that we have over here. That's the reason why these kind of models are usually called additively separable models. Xi and ui both have an impact on the yi that we have over here, but their impact is completely separate. At the moment that I change xi, well, then actually ui has nothing to do with it. And also at the moment that I change ui, well, then xi doesn't have to do anything with that. But that's not what we see over here. Here we do see that at the moment that I'm going to change ui, well, then at that moment in time, actually it also explains how xi is going to have an impact on this yi that we have over here. Well, this model that we have over here, well, we will see that this model is actually much more realistic and many contexts than the model that we had at the previous slide. But before I'm going to do that, I would like to say maybe something which is not that nice with respect to this model that we have over here, and that is that this model by itself is not identified. And the reason behind that is because of the fact that you should realize that at the moment that I have a model like this, and I already know what the beta function is over here, and I also know what the distribution function of ui is, then what I can do is that I could actually change the beta function over here, as well as the distribution function of this ui to another beta function and another distribution function, and still have exactly the same model. So that implies, as we usually say in econometrics, that this model itself is not identified. We cannot actually, well, investigate both this function beta as well as the distribution function. That means that we have to make a normalization. We can make a normalization with respect to beta, but we can also make a normalization with respect to the distribution function of this ui that we have over here. I'm going to choose for the last one. I'm going to choose to have a normalization with respect to the distribution function of ui. Well, that means that we can choose the distribution function ourselves. And if we would like to choose a distribution function, why not then choose always the simplest distribution function? And that's of course the standard uniform distribution function. So I'm going to assume that this thing that we have over here is standard uniformly distributed. Well, let's now go back to the example that I had previous slide, that we are going to assume that the left-hand side that we have over here are going to be log wages, and at the right-hand side we're going to have all kinds of, say, human capital characteristics, including education. Well, let's make it as simple as possible. Let's assume that what we have at the right-hand side, even though we do of course know that there are many more things that are important with respect to the wages, we're just going to have one dummy for college. So SI is now going to be a college dummy. It's equal to 1 in the case that you have a college degree, and it's going to be equal to 0 at the moment that somebody doesn't have a college degree. So then our total model is going to be yi at the left-hand side, log wages at the left-hand side, and beta 0 ui at the right-hand side. So this can be interpreted essentially as the constant, but also you should realize here that the constant actually depends on the outcome of the UI that we have over there. And in addition to that, we also have beta 1 UI times SI. Well, this is actually a very nice equation. Of course, we should realize that in reality, we have to include many, many more x's, but this equation by itself is already quite nice. And the reason behind that is because of the fact that now in this particular situation, we are going to see that the unobserved talents of individuals are going to have an impact on, in fact, how the wages are going to change with respect to the level of education. Now, it is possible that individuals may have a particular draw from UI in such a way that this beta 1 could be very high, and therefore the impact of education is going to be high. And it could also be possible that some other individuals have a particular draw from UI that makes this beta 1 UI to be very small. And that means that these other individuals are going to have much lower returns to education. So therefore we should realize that now, again, UI, even though it's written down over here that it's labor market luck, well, the best interpretation of UI is that it should actually be talents of individuals. Some individuals have particular kind of talents and therefore they have a high return to education, and that is actually important for, well, how realistic this model is going to be. So take into account that even in the case that schooling is exogenous, well, the endogeneity of schooling is definitely an issue, but that's not the main issue here at this particular slide. Even in the case that schooling is exogenous, then we can still expect that, well, education is going to have an impact on the wages in a heterogeneous way. Some individuals are going to have different kinds of returns to education than other individuals. This also has to do a lot with another topic in econometrics which is very important, and that's the literature in treatment evaluation. Well, I'm pretty sure that you must have heard about treatment evaluation before, and therefore I'm also pretty sure that you already have seen this notation before. This notation is usually called the outcome model, or in many situations the causal or even the Rubin causal outcome model. Well, in the treatment evaluation literature, we typically going to assume that we have some kind of variables, SI, that is usually called the treatment variable. And in this case, we are going to assume that it can only take two different values. Either SI is equal to 0, in which case we say that the individual is not treated, or SI is equal to 1, and in that particular situation the individual is going to be treated. And then what we are going to have is that apart from the fact that we observe SI, we're also going to assume that we have another variable, yi, that we observe. The question arises, what is yi? Well, yi is always equal to yi1 in the case that SI is equal to 1, so in the case that individual I is treated, and yi is equal to yi0 in the case that Si is equal to 0. Well, this immediately implies that there is actually a problem with respect to this model that's over here. Reason behind that is because of the fact that we only observe Si and Yi, and we do not observe Yi1 and Yi0, even though Yi1 and Yi0 are actually important for our treatment evaluation. Well, in that sense, it's always good to think about examples. And one of the easiest examples in treatment evaluation is, of course, a medical example. This treatment evaluation literature actually came from the medical literature, and therefore it's usually called treatment because of the fact that in, well, medical sciences, people usually receive a particular kind of treatment for a particular kind of illness. So suppose that what we're going to do is that we're going to look at a group of individuals that have a particular kind of illness or disease. Well, let's look at a very serious disease like cancer. And these individuals are going to either get a treatment or not. So either they're going to have an SI equal to 1 in the case that they receive a treatment, or they have an SI equal to 0 in the case that they do not receive a treatment. Well, and then what we should realize is that yi then is some kind of health outcome. So say after a couple of months, or maybe even a year or a couple of years, we're going to see that we are going to measure the health outcome of the individuals, how well these individuals are doing. Do they still have exactly the same disease, or maybe they're completely recovered? And, well, in some cases, we may be interested in whether these individuals are still alive or not. So, and then you should realize that, well, of course, in order to say something about how important treatment was for these individuals, it would have been nice to know both the health outcome if they would have been treated, as well as the health outcome if they would not have been treated. But we're not able to observe that. You should immediately realize that at the moment that we have somebody who is treated, and we only know the health outcome at the moment that that particular person is treated, but we have no idea what the health outcome would have been in the case that that particular individual would not have been treated. And the other way around, of course, if we have an individual who is not treated, well, then we do actually know the health outcome in the case that that particular individual was not treated, but we have no idea what the health outcome would have been in the case that that particular individual would have been treated. Well, this is a very interesting example, but we should take into account that we can also think of economics example. Even the, say, example that we had in the previous slide with respect to education can be seen as a treatment. We can see education as being a treatment. In that sense, to go back to the example that we had in the previous slide, we can say that SI is equal to 1 in the case that somebody has a university degree, and SI being equal to 0 as an individual that doesn't have a university degree. And then what we can do is that we can ask ourselves the question, well, what is going to happen with your wage? Outcome variable then is going to be the wage. What is going to happen with the wage at the moment that you do have a university degree? Well, then again, you should realize that we, again, have a problem over here, because of the fact that at the moment that we're going to look at somebody that has a university degree, well, then of course we do observe the wage in the case that that particular individual has a university degree, but we have no idea what the wage would have been for that particular individual if that individual would not have had a university degree. On the other hand, at the moment that we have an individual who has no university degree, well, then we do of course know their wages in the case that they do not have a university degree, but we have no idea what the wages would have been in the case that they would have had a university degree. And we should of course realize that in order to get some idea about the impact of the particular treatment, in this case whether somebody has a college degree or not, well, for that we actually should observe both these things that we've over here. Well, before we are going to ask ourselves the question, how could we actually estimate, say, the impact of the treatment, the first question that we should ask is, how are we going to measure the impact of the treatment? Well, one thing we could do is that for every individual, we're going to take the difference between yi1 and yi0. So you could actually say the impact of the treatment. But that, first of all, is going to be hard to do. And maybe then we are going to have many, many different outcomes. So therefore, it's maybe better to simply look at one particular, say, aspect of the treatment that we could have in order to summarize the impact of the treatment. Well, the literature has come up with many, many different of these, say, so-called objects. And one of the objects that is interesting to look at is the so-called average treatment effect. The average treatment effect is actually nothing else as the mean treatment effect among all the individuals. So it's equal to the mean difference between yi1 and yi0, because of the fact that we do know that yi1 minus yi0 is actually the individual treatment effect of every individual that we have in our population. And if we take the mean of it, then we get the so-called average treatment effect. It is essentially what we are going to get at the moment that we are going to take the difference between, well, a situation in which everybody is going to be treated in our population minus what we would have had in the case that nobody would have been treated. It's the average impact that we're going to see among all the individuals at the moment that they are going to be treated. Well, the average treatment effect is a very interesting thing to look at, but we should take into account that in some cases it may not be the best thing to look at. For example, suppose that we are going to look at the, say, impact of universities. You could actually ask yourself the question, what do universities bring to society? Do they really increase the wages of the individual? Well, then of course you could look at the average treatment effect, but you should take into account that what the average treatment effect does is that it looks at the average impact among everybody in the population, including those individuals that actually never went to university. And that implies that it may of course be possible that individuals that never went to university may have a very low return to education. That's probably also the reason that they didn't go to university. And then at that moment in time, we might find out that the average treatment effect is actually pretty low because of the fact that there are some people that went to university that probably had a very high return, but maybe many people that did not go to university that have a very low return of going to university. But that actually doesn't say anything about how much universities actually bring in, how effective universities are, because of the fact that it doesn't matter that much how much people would have been able to increase their wages at the moment that they went to university for individuals that never went to university. So therefore, in many cases, it may be more interesting to look at the so-called average treatment effect among the treated. The average treatment effect among the treated looks a lot like the average treatment effect. Also here, it looks at a mean impact over individuals. But we should take into account that in this particular situation, we only look at the mean impact among those individuals that actually did receive treatment. So for those individuals that have an SI equal to 1. Well, both average treatment effect as well as the average treatment effect among the treated are very popular in the treatment evaluation literature. But the question of course arises, how are we able to estimate them? Well, the answer to that particular question is actually related to the model that we have in mind. Well, so far we have been looking at two different models. We have looked at the standard linear regression model, and we have also been looking at the random coefficients model. Let's start with the simplest of the two, and that's the standard linear regression model. If we're going to go back to the this slide that we had over here, then at the moment that we would like to do that for the simple treatment evaluation model, then what we have is only two outcomes, SI equal to 1 and SI equal to 0. So we simply are going to have a regression where at the left hand side we have YI, and on the right hand side we have beta 0 plus beta 1 SI plus UI. So one regressor which is either equal to 0 or 1 depending on whether you are treated or not. Well, based on this, it is not that difficult to see that there are two potential outcomes for every individual. Either your S is equal to 1 or your S is equal to 0. And that is of course related to the yi1 and yi0 that we've over here. So yi1 is now equal to beta 0 plus beta 1 plus ui. Simply substituting in si equal to 1 in this right hand side of this equation. And well, in addition to that, we have yi0 is equal to beta 0 plus ui. Well, based on this, it's not that difficult to understand that if we are going to substitute this, well, first of all, we could actually subtract these things over here. Then we get simply beta 1. And then if we're going to substitute it is in either in the equation of the average treatment effect or the average treatment effect among the treated, that in both cases we simply get here beta 1. Then we also get beta 1. So both the average treatment effect as well as the average treatment effect among the treated, they're equal to beta 1. We actually also know how to estimate this, at least at the moment that S and U are uncorrelated with each other, because of the fact that you know already from the very first year that in that particular situation, we can simply use an ordinary squares regression of y on this S in order to consistently and unbiasedly estimate this beta 1 that we have over here. So that is pretty simple. However, the question of course arises, what is going to happen at the moment that S and U are going to be correlated with each other? Well, then it becomes a lot more difficult. Then it is no longer possible to simply run an ordinary squares regression of yi on this Si that we've over here and estimate the beta 1. Well, it's still possible to do that, but we do know that that will result in biased and inconsistent estimators. So the question then arises, what can we do instead of that? Well, you do already know the answer to that. That's IV. We could use IV estimation in order to estimate, again, both the average treatment effect as well as the average treatment effect among the treated, while estimating this beta 1 that we have over here. Well, I know that you have already seen IV many times before, but let's look at a very simple example to see what we actually do at the moment that we're going to use instrumental variable estimation in this particular case. Let's assume that we have a binary instrument. So Z can only take two values. Z is either equal to 0 or it's equal to 1. Well then, and I'm not exactly sure whether you have seen this many times before during your, say, during other lecture series, but what you should realize is that IV is actually based on the fact that we are going to look at the mean of yi, the conditional mean of yi, conditional on zi. And that's very special because of the fact that you should realize, and we will use that often again, is that at the moment that we're going to use standard linear regression analysis, so ordinary squares is always based on the conditional mean of yi conditional on s. Ordinary squares tries to estimate the conditional mean of y conditional on this s that we have over here. That's what you always have to understand in order to understand ordinary squares. But IV doesn't do that. IV instead says like, well, let's do another route, and let's not look at the conditional mean of y conditional on s, but let's look at the conditional mean conditional in this case on the outcomes of z. Well, z can take two outcomes, either z is equal to 0 or z is equal to 1. Let's first of all look at the mean of yi conditional on zi equal to 1. Well, then what we get at the right hand side is beta 0 plus beta 1 times the mean of si conditional on zi equal to 1, plus of course the mean of ui conditional on zi equal to 1. Well, then we are going to make two assumptions with respect to this z. First of all, we are going to assume that this thing that we have over here, the mean of s conditional on zi equal to 1, we cannot just write it as the mean of s. That's instrument relevant. And another assumption that we're going to make is instrument exogeneity. And that is that we are going to assume that this mean that we have over here is equal to 0. So we can also write this simply in this form that we have over here. Well, we can do exactly the same thing at the moment that we're going to look at the mean of yi conditional on zi equal to 0. That's equal to the right hand side that we have over here. Well, then what we can do is, based on these two restrictions that we have over here, these are two restrictions in two unknowns, beta 0 and beta 1. Well, then it's not that difficult to see that solving for beta 1 will in the end give us, well, that the IV estimator at least tries to estimate the mean of yi conditional on zi equal to 1 minus the mean of yi conditional on zi equal to 0 divided by the mean of si conditional on zi equal to 1 minus the mean of si conditional on zi equal to 0. That is what the IV estimator tries to estimate. Of course, it doesn't estimate itself because of the fact that these means that we have over here, they're unknown to us. These are population means, and population means generally are unknown to us. But what we can do, and that's exactly what we would do in this particular case, is that we can replace them by their corresponding sample means. We can look at our sample and look at the mean of yi among the subpopulation that has a zi equal to 1, you can look at the mean over the subpopulation that has a zi equal to 0, and here we can do exactly the same thing. And then we get our, say, famous IV estimator. We do know that the IV estimator is biased, but fortunately it is actually consistent. So we can get consistent estimators of, say, the average treatment effect as well as the average treatment effect among the treated. But now we should realize that we could, this was the most simple model, of course, this was the linear regression model. But we can, of course, do exactly the same thing, or ask ourselves whether we can do exactly the same thing at the moment that we're going to look at the so-called random coefficients model. Well, that was the model that we had a couple of slides back. That was this model that we have over here. Then this model is now going to be the model that we are interested in. Well, also here we would like to look at yi1 and yi0. Well, again, the only thing that we need to do is, first of all, yi1, simply substituting here at the right-hand side a 1 for si, so we get beta 0 ui plus beta 1 ui, and by, well, yi0 simply is equal to beta 0 ui. So therefore, at the moment that we would like to look, for example, at the average treatment effect, well, then we're going to get the mean, well, difference between these two things that we've over here. yi1 is equal to beta 0 ui plus beta 1 ui, as I just said, and yi0 is simply equal to this beta 0 ui that we've over here. Well, the beta 0 ui's, of course, are going to cancel to each other, and therefore in the end what I'm going to get is the mean of beta 1 ui. And that actually makes sense because of the fact that you should realize that, as I have already said a couple of times, the beta 1 in this particular model is in fact measuring, or maybe better to say beta 1 ui, is measuring the individual impact that, say, treatment has in this particular case. And therefore, at the moment that we would like to look at the average treatment effect, then we take the average over the individual treatment effects that we have over here. Well, we can do exactly the same thing at the moment that we're going to look at the average treatment effect among the treated. It should not come as a big surprise that that is actually equal to the mean of beta 1 ui again, but now conditional on si equal to 1. Now a question arises, based on these two things that we have over here, could we actually estimate these things using ordinary squares? So could we just, again, run a regression of ordinary squares and then get back to the model, well, estimate in fact these things that we have over here, or at least one of these things? Well, then what we need to do is that we have to now look at what ordinary squares actually estimates in this case. Well, ordinary squares at least tries to estimate, and this is something that you must have seen many, many times before, the moment that you have a, say, single regressor, and that regressor is going to be dummy variable, well, then it's not that difficult to see that the mean of the estimator of ordinary squares is always going to be equal to the mean difference in terms of the conditional means, in this case the mean difference of y conditional on si equal to 1 minus the mean of y conditional on si equal to 0. That's this mean difference that we have over here. Well, and then the question arises, what is this thing that we have over here? Well, the first thing that we can do is that we can substitute in, say, well, first of all, we should realize that this, of course, this thing that we have over here is simply equal to yi1 because of the fact that we know that si here is equal to 1, and here we get yi0. So therefore, what we can do is that we can simply substitute in yi1 and yi0, then we get here beta 0 ui plus beta 1 ui, and here we get simply beta 0 ui. Well, then the next thing that I can do is that I can, of course, realize that this is a, well, mean of a sum, these two things that we have over here, so we can always write that as a sum of means. But what I'm going to do as well is that I'm going to take the beta zeros together in order to write it in the form that we have over here. So ordinary squares, well, tends to estimate this thing now that we have over here. And the question, of course, arises, could that be possibly equal to any of these things that we have here at the right hand side? The answer to that is of course no. This is quite different from the things that we have over there. However, one thing we could actually say is that this final term that we have over here, well, that actually is exactly equal to the average treatment effect among the treated. We see over here. That's not that difficult to see. However, you should realize that that doesn't help us at all, because of the fact that from ordinary squares, we do not actually get all these three terms together. What the only thing we're going to get is just one particular term, which is just, well, the sum of all these terms that we have over here. So we are not able to get any information about these terms separately. The only thing that we're going to get is the sum over all these terms together. So therefore, ordinary squares is not going to give us any information generally about this last term that we have over here. Of course, unless we are going to make, well, be in a situation in which these two terms are going to cancel to each other. If these two terms are exactly identical to each other, well then of course they're going to cancel, and then we immediately see that what ordinary squares tries to estimate is exactly this last term that we have over here, which is exactly equal to the average treatment effect. The average treatment effect among the treated. However, the question arises, in which cases are these two things equal to each other? Well, that's only the case at the moment that U and S, they are independent from each other. Because of the fact that if they're independent from each other, well, then you should realize that I don't have to condition them anymore on Si equal to 1, neither on Si equal to 0. And that means, of course, that then these two things, they are equal to each other, and therefore they're going to cancel to each other. Take into account that in this case, I need independence, and the reason behind that is because of the fact that, well, uncorrelated is not enough in this particular case. And the reason behind that is because of the fact that we do not know how this function looks like. If this would be a linear function, then of course we could say that U and S only have to be uncorrelated with each other, but this could be a very complex function with respect to U. And in that case, well, generally what we need is independence. Take into account that that assumption is even much stronger than the standard exogeneity assumption, which only assumes that U and S should be uncorrelated with each other. So therefore we are going to see that in order for, say, ordinary squares to estimate consistently the average treatment effect, the average treatment effect among the treated, we need this rather strong assumption that we have over here. Well, in addition to that, we can also say that at the moment that we are going to have that S and U are independent from each other, well then actually this last term that we have over here is not only the average treatment effect among the treated, but it's actually also in that particular situation the average treatment effect itself. And the reason behind that is because of the fact that if U and S are independent from each other, well then at that moment in time, of course we can also get rid of this Si equal to 1 over here. And then we should realize that ordinary squares not only estimates the average treatment effect among the treated, but also the average treatment effect. But the main question that arises right now, is it a good assumption to make that U and S, they are independent from each other? Well, the answer to that is of course not. What we should realize is that in social sciences, it is in many cases the situation that treatment actually depends on the behavior of individuals. That is to say, that people can actually make decisions about their treatment. At the moment that we're going to think about the schooling example that we have seen before, then you should realize that individuals that have a relatively high return to education are also the individuals who are more likely to actually educate themselves, that are more likely to go to university. And that means, of course, that we, given the fact that UI actually says something about, of course, the returns to education, we can expect that, well, whether people are treated or not, so whether, well, Si is equal to 1 or 0, depends actually quite a lot on the, say, UI, the unobserved talents that individuals have that make them to have a high return to education. So therefore, the assumption that UI and SI should be independent from each other, well, that particular assumption is almost never going to be true in social sciences. In medical sciences, you might say exactly the same thing. In medical sciences, at the moment that you're going to look at individuals who are going to get a treatment or not, then also there you can expect that the individuals that expect the most out of the treatment are more likely going to have a treatment than individuals that do not expect that much out of a treatment. So also there you should realize that it's generally not true that U and S are going to be independent from each other. Of course, unless you are going to make yourself U and S to be independent from each other, as you typically do in the so-called random control trials. In a random control trial, what you're going to do, and that's, well, very much the case in almost any medical sciences research, what you're going to do is that you're the one that is going to make the decisions about S. So then what we typically do in medical sciences is that we are randomly going to give, say, a particular group, a particular kind of treatment, and randomly some other group, which is usually called a control group, are not going to receive the treatment. Well, in that sense, you then always know that U and S are going to be independent from each other, and then of course we are able to use ordinary squares to estimate the average treatment effect, as well as the average treatment effect among the treated, even in this random coefficients model. But you should take into account that actually in economics or generally in social sciences, even though also there it's a good idea to use random control trials in order to do these kind of things that we have over here, in many situations it may not be possible, or at least very difficult, to run random control trials. Well, before I'm going to answer the question what we could do in this particular case, or what tools do we have as econometricians to do something about this, before I'm going to answer that particular question, let me first look a little bit more into the question, why does ordinary squares have a bias for the average treatment effect? Or actually, in this case, first of all, we're going to look at the average treatment effect among the treated. Well, in order to answer that particular question, the first question that we have to ask, what is actually the bias with respect to ordinary squares with respect to average treatment effect among the treated? Well, what we do know is that the mean of ordinary squares, the mean estimator of ordinary squares, is this thing that we have over here. And what a bias is that it's usually the difference between, well, what you estimate, or the mean of what you estimate, this thing over here, minus what you intend to estimate. That's in this case the average treatment effect, so that's this thing that we have here at the right hand side. Well, if we take the difference between this and that, then these two terms are going to cancel, or this term is going to cancel. That means that the only two terms that we still left with are these terms that we have over here. Well, these terms, the interpretation of these terms is that it's actually the difference between the mean outcome of the individuals in a treatment group if they would have not have been treated, minus the mean outcome of the individuals in the control group at the moment that they would not have been treated. We should realize that this thing that we have over here is observable because of the fact that individuals who are in the control group who are not treated, well, we can know what they actually got at the moment that they were not treated. That's actually what we observe. So therefore, what we can do in order to estimate this thing over here is just take the mean over their observations. However, this thing that we have over here, well, we cannot get any idea about it because of the fact that we should realize that we do not actually know what the outcome of the, say, treatment group would have been in the case that they would not have been treated. So we can also not take the average outcome over this particular group. Well, then you should realize that, of course, there are techniques in order to try to still estimate the, say, average treatment effect among the treated. And the ordinary squares tries to estimate the average treatment effect among the treated, which is of course nothing else as the mean outcome, well, for the individuals in a treatment group if they would have been treated, minus the mean outcome if they would not have been treated. Well, this last thing, it is actually not possible to know that because of the fact that that's not something that you get from the data. But what ordinary square says is like, well, maybe we can, well, substitute the mean outcome for the treatment group in the case that they would not have been treated. Maybe we can replace that by the mean outcome for the, say, control group at the moment that they're not going to be treated. That's what ordinary squares try to do. And you should realize that that actually might not always be true because of the fact that we should realize that in many situations it may be possible that the mean outcome of the treatment group in the case that they were not treated is different from the mean outcome of the control group. At the moment that we're going to again look at a couple of different examples, let's first look at another economic example. Suppose that we're going to look at job training programs in which unemployed individuals may be trained in order to find back re-employment. Well, in that particular case, you should realize that there are generally different kinds of unemployed individuals. You have the very motivated unemployed individuals that, even though they're unemployed, would like to, well, find back re-employment very soon, and therefore they try to do everything to find a job. And you have individuals that are not that motivated, and these are typically individuals that have the idea that they will not be able to find a job at all, or they don't mind that much that they're unemployed. Well, we know of course that the first group, the motivated ones, have a very much higher likelihood of finding back re-employment than the second group in general, no matter whether they are going to have a job training program or not. However, at the moment that individuals have the decision to make to go to a job training program, you would expect that the motivated individuals are much more likely to go for, say, a job training program than the not so motivated individuals. So that implies that, well, the group of individuals that are going to be, say, participating, that have an SI equal to 1, would have already a much higher likelihood of getting out of unemployment, even in the case that they would not have been treated. So therefore, in that sense, the likelihood of getting out of unemployment of the treatment group, even in the case that they would not have been treated, was already higher than that of the control group. Something like that you would also see at the moment that you would look at cancer patients. Also at the moment that we're going to look at cancer patients, it may be possible that it's going to be a selective kind of group that are going to be treated. It could be possible that, well, medical doctors actually only going to treat the individuals that are really, really ill. Suppose that you have a particular kind of treatment which is maybe very expensive and, well, maybe also very painful, maybe not so nice to have. Then at that moment in time, you might only give it to the individuals that are very, very ill, because of the fact that if you're going to give it to individuals that are not that ill, well, maybe that's not that great. Maybe you spend a lot of money actually on individuals that would actually survive anyways. So therefore, you would in this particular situation see that the individuals that actually receive treatment, well, they would have generally had a much worse outcome at the moment that they would not have been treated than the individuals that are not treated at all. And therefore also here you're going to see that, well, you're going to have a bias at the moment that you're going to use ordinary squares. Now the question arises, why does ordinary squares have a bias for the average treatment effect? Well, for that, remember that ordinary squares tries to estimate this thing that we have over here. That's a thing that we have already seen a couple of times before. And then we should also realize that that implies, of course, that the bias term that we're going to get is equal to these terms that we have over here, minus, of course, what you intend to estimate, and that is this mean that we have over here. Well, it's immediately clear that the first two terms that we have over here, that was already the base term of the average treatment effect. So that implies that the bias, the total bias of the average treatment effect, is going to be equal to the average treatment effect, the bias of the average treatment effect among the treated. But we have an additional term over here. And the interpretation of this impact that we have over here is related to the fact that the average treatment effect among the treated is generally different from the average treatment effect. And that's because of the fact that generally we might expect that the impact among those individuals that are treated is different among the impact of the individuals who are not treated. Also here you should realize that this generally may not be equal to 0. And the reason behind that, for example, at the moment that we are another time going to look at cancer patients, then it may be possible that, say, individuals who are going to, well, receive treatment, well, generally they will only receive treatment at the moment that the medical doctor has the idea that you are going to have a very high benefit from treatment. Suppose another time that we're going to look at cancer patients, and suppose that, well, a particular medical doctor decides that one particular individual has such a low return or impact from a particular treatment, such as, for example, a chemo, then this particular individual will not generally receive that, say, treatment simply because of the fact that receiving a chemotherapy is something which is very costly, not just in monetary cost, but also in terms of the individual. It's very bad to have a chemotherapy. So therefore, at the moment that the returns are not that high, then generally you're not going to receive such a treatment. But that means, of course, that the individuals that receive a treatment generally have a higher, say, return than the individuals that do not receive a treatment, and therefore we're going to get this additional bias. Now that we know that ordinary squares is inconsistent and biased for both the average treatment effect as well as the average treatment effect among the treated, the question now arises, what can we do about this? Well, an answer to that question could be that we do exactly the same thing as in the linear regression model and start to try to estimate this model with respect to IV, instrumental variable estimation. In order to do that, I'm going to introduce an instrument, and again this instrument is going to be binary, so Zi could either be equal to 0 or 1, and remember that Si, of course, was our treatment variable, which is either equal to 0 at the moment that you do not receive treatment, and 1 in the case that you receive treatment. Then we're going to use the following definition. Si is now going to be equal to Si1 in the case that Zi is equal to 1, and it's going to be equal to Si0 in the case that Zi is equal to 0. Well, take into account that because of the fact that Si can only take values equal to 0 and 1, that also of course holds true for Si1 and for Si0. However, we allow for the fact that for some individuals, Si1 and Si0 may be different from each other. For example, it may be possible that Si1 is going to be equal to 1 and Si0 is going to be equal to 0. Well, then based on a Nobel Prize winning article, well, this is from Engrist and Imbens. It's actually a pretty old article from 1994. It's especially interesting for the Dutch students over here. Well, last year, well, actually not the last year 2022, but 2021, the persons who won the Nobel Prize, well, half of the Nobel Prize went to David Card, and the other half went to two persons, Engrist, who is from the United States, and Guido Imbens, who is originally from the Netherlands. Well, based on this particular article, these two guys, they define the following groups based on the potential combinations that you can actually have with respect to Si1 and Si0. First of all, we have the so-called compliers, and compliers are individuals that have an Si1 equal to 1 and an Si0 equal to 0. Well, these are individuals that will actually be treated at the moment that their Z is equal to 1, and they will decide not to be treated at the moment that Zi is equal to 0. These are the so-called compliers. So for these individuals, it's clear that actually whether they're treated or not depends on their outcome of Z. Apart from the compliers, we also have the always takers, and always takers are individuals that will always be treated. So that implies that their Si1 is equal to 1 and their Si0 is also equal to 1. So that means that, well, they are going to be, well, always being treated no matter what the outcome of Z is going to be. And apart from the always takers, we also have the so-called never takers. And never takers are individuals that have an Si1 equal to 0 and an Si0 equal to 0 as well. These are individuals that never are going to be treated. So these are individuals that never receive treatment, well, actually completely independent of the value of Z that they have over here. And then finally we have the defiers, and defiers are individuals that are completely opposite to the compliers. Their Si0 is equal to 1 and their Si1 is equal to 0. So these are individuals that will be treated at the moment that their Zi is equal to 0, and they will not be treated at the moment that their Zi is equal to 1. Well, in order to make this, well, analysis a little bit more simple to understand, one thing they can do is that you can think of Zi as being the intention to treat. This is especially interesting at the moment that we're going to think of a medical, say, evaluation, a medical experiment. Then it may be possible that individuals are going to receive some kind of treatment, some kind of, for example, they're going to receive some kind of pills, and individuals, of course, at the moment that they prescribe these pills, then they can still decide to actually take these pills or not. Well, suppose that we know whether somebody gets prescribed the pills, that is equal to 1 in the case that Zi is, well, Zi is equal to 1 in the case that you're going to be prescribed the pills, and Zi is equal to 0 in the case that you're not going to be prescribed the pills. And suppose that we also know whether actually the pills were also taken by the individual patient. So then, well, if they take the pills, then Si is equal to 1 and Si is equal to 0 in the case that you decide not to take the pills. Well, that is intention to treat. Also in economics, we sometimes can think of intention to treat itself, but we can also think of other situations. For example, we can think of an example that's very relevant for many of you, and that is that you should realize that in the Netherlands for a long time we had a so-called scholarship at the moment that you decided to go to university. That scholarship was pretty high in the 1970s. It was as high that you could almost easily live on a scholarship. You didn't have to work at all, and you could actually quite easily find a room or maybe even a whole apartment that you could actually rent from your scholarship. Then in the 1980s and the 1990s, as well as in the 2000s, this scholarship was actually quite well reduced. And then somewhere in the 2010s, well, I have not been that often in the Netherlands the last couple of years and I haven't been a student, but as far as I know, in around 2015, then at a particular moment in time, this scholarship was completely abolished. And then for a couple of years, say the last 5 to 8 years, there has not been a scholarship, but if I'm correct, as far as I know, well, now the scholarship has been re-established. Well, that means, of course, that based on the year that you become 18, well, the year in which you were born, but also the year in which you become 18, well, you are going to either have a scholarship or not. If you're, say, born in a period in such a way that you will be, for example, 18 in 2010, well, then that was a time that you still received a scholarship, and therefore you, at the moment that you have to make a decision in order to go to university, then you actually expect that you will receive that scholarship for the whole period of time. However, suppose that you actually turn say 18 in the year 2015, then you do know that you do not receive a scholarship, and that of course is going to have an impact on, in the end, the likelihood that you're going to go for university. So therefore, ZI in this particular case can be seen as a very interesting, say, instrument based, of course, in the year that you're going to turn 18. Well, then what we're going to do is that we're going to make a couple of assumptions. First of all, I'm going to assume that UI, SI1 and SI0, they're going to be independent from the Z, so from the instrument. You should realize that this is actually quite like what we usually have at the moment that we think about instrument exogeneity. You should realize is that, that SI1 and SI0 are here assumed to be also independent from Z. Well, that is only the SI1 and SI0 itself, of course. Of course, SI itself does depend on Z because of this relationship that we've over here. But apart from that, we also need independence between the U and the Z that we have over there. Then in addition to that, we also have the assumption that the probability that SI1 minus SI0 is going to be different from 0, that must be larger than 0. What does this mean? Well, this actually means nothing else is that we are going to assume that, well, there are going to be either compliers or defiers, and that our, say, population or our data set does not only have always takers or never takers. It means actually nothing else is that, well, there must be some individuals that actually are going to change the behavior based on the value of Z that we have over here. Well, this is related to what we usually have in standard instrumental variable estimation as being instrument relevance. It must be the case that for some individuals, the decision of whether you're going to be treated or not must actually be dependent on the value of the Z that we have over here. That is nothing else than saying that Z must actually have an impact on, well, the decision of whether you're going to be treated or not. It must have an impact on this SI that we have over here. So this is actually, this thing that we have over here is related to instrument exogeneity in a standard instrumental variable technique or in a standard instrumental variables framework. And this thing that we have over here is related to instrument relevance. Now, of course, the question arises, what is IV now going to estimate? Well, what we already know from a couple of slides back is that IV tries to estimate a numerator divided by the denominator. Let's first of all look at the numerator. That's this thing that we have over here. The mean of yi conditional on zi equal to 1 minus the mean of yi conditional on zi equal to 0. What we can now do is that we can now substitute in, of course, the model, and then we get this relationship that we have over here. yi1 is, of course, equal to this thing, or yi is, of course, equal to this thing over here. So beta 0 ui plus beta 1 ui si, and we actually also have it over there. Now, in this case, we cannot, well, immediately realize that this si is equal to 1 and that si is equal to 0, because of the fact that we no longer condition how on the si's, but we actually condition here on the z's. So that is not possible. But what we can realize is that this si is, of course, equal to si1, and this si is equal to si0, based on the notation that we had at the previous slide. And then what we can do is that we can now use this assumption over here, this assumption of instrument exogeneity, which actually implies that both ui as well as si1, they're independent from zi. So therefore, we can get rid of this zi equal to 1 over here. And for the same reasons, we can also get rid of this zi is 0 over here. So therefore, we can also write it like this. Well, and then what we can do is that we can now realize that we now no longer condition on anything. So we can take these two means together. And if we're going to rewrite it a bit, then finally what we're going to get is the mean of beta 1 ui multiplied by si1 minus si0. Well, this actually looks very, very nice, but we should realize that I'm going to rewrite it a little bit more in a way that it's not going to look so nice anymore, but it's going to have a better interpretation. What we should realize is that Si1 minus Si0, well, it is only going to be different from 0 at the moment that we either have compliers or defiers. So at the moment that either Si1 minus Si0 is equal to 1 in the case of compliers, or at the moment that this thing is equal to minus 1 in the case of defiers. At the moment that we have always takers or never takers, then this thing is simply equal to 0. That implies that what we can do is that we can use, well, the law of iterated expectation and condition on the different potential outcomes of this thing that we have over here. Take into account that if we have a 0, then this whole thing is going to be equal to 0, so that we don't have to take into account. But what we can do is that we can, well, condition first of all on Si1 minus Si0 equal to 1. So then we get the mean of beta 1 ui multiplied by 1, of course, conditional on Si1 minus Si0 equal to 1, multiplied, of course, by the probability that Si1 minus Si0 is equal to 1, plus then, well, the mean that beta 1 ui, or the mean of beta 1 ui, conditional on Si1 minus Si0 equal to minus 1, and multiplied by this probability that we have over here. Well, this we will actually keep like this, but we can do exactly the same thing with respect to the denominator. Here we know that the denominator is equal to this thing over here, and again what we can do is that we can replace this Si by Si1, and this Si that we have over here we can replace it by Si0. So then we get all these things that we now have over here. And then we should realize that, well, again, Si is independent from Z, so we can get rid of this thing over here, and Si0 is also independent from Z, so we can get rid of this thing that we've over here. So therefore, in total, we're going to get this thing now that we've over here. And this can actually now be written as, well, what we have is that this is either equal to 1, in the case that Si1 minus Si0 is equal to 1, so we get the probability Si1 minus Si0 equal to 1, minus the probability that Si1 minus Si0 is equal to minus 1. So therefore, we now get, for the denominator, we get this thing over here. Well, and that means, of course, that the IV estimator tries to estimate this completely meaningless object that we have over here. Take into account that this is completely meaningless because at the moment that, for example, we're going to look at the numerator, well, what is this thing over here? Well, I have no idea. It's something like, well, first of all, this thing that we've over here is the mean impact among the compliers multiplied by the probability to have a complier minus the mean impact among the defiers multiplied by the probability that we have a defier. Well, that doesn't say anything, even in the case that both of these things are going to be positive, so there's a positive impact. Well, IV may actually give me a negative thing over here. So therefore, I have no idea what actually IV tries to estimate. However, in the case that we make one additional assumption, namely that the probability that Si1 minus Si0 is equal to minus 1 is equal to 0, is usually called a monotonicity assumption, then we can do a little bit more. But before I'm going to show that, the question of course arises, what is this assumption? Well, this assumption actually says nothing else as that we rule out the possibility that there are so-called defiers. So that implies that going back to this slide that we have over here, I'm going to allow for the fact that there might be some always takers and never takers. Of course, there should always be some compliers, but I'm going to rule out that there might be any defiers. The question whether that is going to be an acceptable restriction depends actually on the application. If, for example, are going to think about the intention treat, where individuals are going to receive pills, well, then you should realize that, well, defiers, what are actually defiers? Well, defiers are individuals that at the moment that they get prescribed pills, then they decide not to take them, but at the moment that they're not going to be prescribed pills, then they will actually take those pills. Well, it might even be very difficult to actually take pills at the moment that you even do not get them prescribed. So in this particular case, it may actually be very likely that they're not defiers. Then, at the moment that we're going to look at this example that we have over here with respect to going to university based actually on a scholarship, well, then the defier is going to be somebody who decides to not go for university at the moment that they receive a scholarship, but these individuals would have actually gone to university at the moment that they do not receive a scholarship. Well, again, that doesn't seem to make any sense. Why would you actually decide to not go to university at the moment that you get the scholarship and then decide to go to university at the moment that university even becomes less attractive without a scholarship? So therefore, also for this particular application, it is easy to rule out the possibility that you have defiers. Well, if there are no defiers, well, then we can actually rewrite this equation that we have over here. Then what we should realize is then that, well, first of all, these two probabilities, they're going to be equal to 0. That means, of course, that this whole thing we have over here is going to drop out. But also these two things are going to drop out, and that implies that IV simply is going to now estimate this thing that is over here. And what is that? Well, that's actually nothing else, the average impact among the compliers. Well, Angus and Imbens call this the local average treatment effect. Based on this, we can draw two conclusions with respect to IV estimation. That is, first of all, that IV needs additional assumptions. Apart from the standard assumption of instrument exogeneity and instrument relevance, we actually need, in this case, independence, and also we need this monotonicity assumption that I've just made. But maybe even more important, you should realize that the local average treatment effect, or LATE, or actually what is estimated by IV, which is exactly the same, depends actually on the chosen instrument. You should realize that actually this thing that we have over here depends on who is going to be a complier and who is not going to be a complier. That implies that we can have the following situation. Suppose that we have two researchers, researcher number 1 and researcher number 2. And suppose that they actually have exactly the same kind of model in mind. They want to estimate exactly the same thing. They want to estimate the same impact from the same treatment. But suppose that, say, researcher number 1 is going to use another instrument than researcher number 2. Well, then it's possible that at the moment that they're going to use IV, that both of the researchers are going to have different outcomes. They're going to have different LATEs because of the fact that LATE depends on the instrument, and that means that if you have a different instrument, then at that moment in time, you also have a different value of LATE. Well, it could be so extreme that the first researcher is going to find a positive impact, whereas the second researcher is going to find a negative impact. That's not very likely to be true, but generally the outcomes are going to be different. And that's not because of the fact that the first researcher has done something wrong and the second researcher didn't, but it's because of the fact that LATE actually does depend on the instrument. So at the moment that you take another instrument, then you also get actually another LATE. That is somewhat related to the fact that you should realize that LATE by itself is not policy relevant. You should realize that average treatment effect, as well as the average treatment effect among the treated, is something which is, well, related to policy, but that's actually not related to the local average treatment effect, or at least the local average treatment effect is not at all interesting for the policymaker. It looks at the average impact among the compliers, but compliers are related to the instrument, to the chosen instrument, and they're not interesting for the policymaker itself. Well, that's the reason why Heckman and Vidlasil, in an Econometrica paper in 2005 will introduce objects that are policy relevant, but I'm not going to discuss this article over here. I would like to go on with a numerical example. Then first of all, we have this equation that we have already seen a couple of times before. In addition to that, we are going to introduce an additional variable, SI star. That's this one that we have over here, and it's defined to be equal to minus a half plus a half times Zi plus Vi. And Zi is going to be equal to an indicator function that indicates that EI should be larger than a half, where I'm going to assume that EI is going to be uniformly distributed. So that essentially means nothing else is that randomly we are going to have that 50% of the population is going to have a Zi equal to 0 and 50% randomly is going to have a Zi equal to 1. And then finally we're going to see that this Si that we have over here is going to be equal to 1 at the moment that the right hand side, so Si star, is going to be positive, otherwise it's going to be equal to 0. Then we have the definitions of yi0 and yi1, and then I would like to say something about the distribution of ui and vi. I'm going to assume that both ui and vi, they are going to be, well, uniformly distributed, but I allow for the fact that they may be correlated with each other. And this correlation I'm going to determine by this so-called FGM copula. Copula, I'm not sure whether you have ever heard about that before, but these are nothing else as distribution functions of, say, factors that are going to be uniformly distributed, but are allowed to be correlated with each other. Well, the FGM copula has a distribution function that looks like the one that we have here at the right hand side. And a special thing with respect to this FGM copula is that you should realize that at the moment that theta is equal to 0, well, then we have independence. That's immediately clear because of the fact that then this whole thing that we have here is going to drop out completely. And then what we're going to have is just u times v, which is actually nothing else as a distribution function of two uniformly distributed random variables that are independent from each other. Then the next thing we can do is that we can now define beta 0u and beta 1u. I'm going to assume that they are both going to be parabola with different parameters. And that immediately implies that we can, based on this, well, look at yi0 as well as yi1. They're defined to be equal to these things that we have over here, based on these restrictions that we have over here. And we can even look at beta 1, which is now going to be equal to this thing that we have over here. Well, for that we can look at a picture. Here we have on the x-axis we have the different values of u. Take into account that every individual is going to randomly draw a u which is going to be uniform, of course. So therefore we are going to simply have for every individual a particular level of u, and it doesn't really matter whether you're going to have any of these different outcomes. But we can, of course, first of all look at the outcome at the moment that you're not going to be treated, that this thing that we have over here. We immediately see that the larger you draw from u is going to be, also the larger is going to be, in this particular case, the outcome that you're going to have in the case that you're not treated. Well, that's actually not only true for yi0, it's also true for yi1. And we even see that the difference between yi0 and yi1 becomes actually larger as u becomes larger, and that implies that we now also see that the impact actually increases at the moment that u becomes larger. So that implies that also individuals that have a relatively large u are going to have a higher impact. Well, based on this, we can calculate the average treatment effect as well as the average treatment effect among the treated. Let's first of all look at the average treatment effect. That's of course by definition equal to this thing that we have here on the right hand side. This is a mean, of course, and based on that we can look at an integral over the uniform distribution of beta 1. Well, that's not that difficult. We then have to substitute in the definition of beta 1, that's equal to this thing over here, and then it's not that difficult to actually calculate that the average treatment effect in general is going to be equal to 5 over 3. That's equal to 1 and 2/3. We can do exactly the same thing with respect to the average treatment effect among the treated. That's by definition equal to this thing over here. However, calculating the average treatment effect among the treated is actually somewhat harder. So I'm not going to do all the calculations over here, but I actually did put a note on Brightspace that actually explains how to actually calculate the average treatment effect among the treated, well, in a more general way. But here we have that also the average treatment effect among the treated equal to 5/3, so another time 1 and 2/3, plus an additional term which is equal to 1/18 times theta. It's immediately clear that at the moment that theta is equal to 0, then the average treatment effect and the average treatment effect among the treated, they are identical to each other. And that makes sense because of the fact that if theta is equal to 0, well, then you should realize that based on this model that we have over here, well, then actually there is the individuals that are treated are completely randomly treated because of the fact that if U and V, they're independent from each other, well, then individuals simply are going to, well, get a random draw from V, which is not related to that U over there. So therefore, there's completely random treatment. And if there's random treatment, then the individuals who are treated are no different from the individuals who are not treated, and that implies that the average treatment effect among the treated, they should be equal to the average treatment effect itself. However, at the moment that theta is going to be positive, then we actually see that the average treatment effect among the treated is larger than the average treatment effect. Well, that is quite easy to explain why this actually should be true, based on the model that we have had. What we should realize is that based on this equation that we have over here, that in order to be treated, you must have a relatively high level of V. Reason behind that is because of the fact that in order to be treated, Si star must be larger than 0. And that means, of course, that this thing must be positive, and therefore V must be quite high. So that implies that by definition, individuals who are treated have a very high level of V. But at the moment that there is positive correlation between V and U, that means, of course, that also these individuals are going to have relatively high levels of U. Well, that means in terms of this picture that, well, the individuals who are treated are generally more likely to be here at the right-hand side than here at the left-hand side. And that means that at the moment that we're going to look at the average treatment effect among the treated, then we are going to take an average over the individuals over here, whereas at the moment that we're going to look at the average treatment effect, then we take the average over the full population. So that implies that it makes sense that since the treated individuals are the ones with a higher, say, betas, the higher impacts, that therefore the average treatment effect among the treated should be larger than the average treatment effect. Well, then what we can do is that we can go on with ordinary squares. Well, at the moment that we're going to calculate the things for ordinary squares, again, that is actually takes some mathematics, but you can show that then ordinary squares is equal to 5/3 another time plus 13/90 multiplied by theta. That means immediately that the bias term of the average treatment effect among the treated equals 8/90 times theta. That means that ordinary squares overestimates the average treatment effect among the treated, at least at the moment that theta is going to be positive. Well, again, that is quite easily explained by looking another time at the figure that we have at hand. What is the average treatment effect? Well, generally the average treatment effect among the treated is of course nothing else as, well, we do already know that individuals who are treated generally are here at the right hand side. And what you should realize is that what we then have to do is that we have to look at the average outcome among those individuals who are treated minus the average outcome that they would have had in the case that they would not have been treated. But that last thing, we cannot actually calculate that. And what ordinary squares does is that instead it's going to take the average outcome among those individuals who are not treated. But we should take into account that individuals who are not treated, usually are more over here. So that implies that we take the average over the individuals over here minus the individuals over there in order to estimate the average treatment effect among the treated at the moment that we're going to use ordinary squares. Well, that's of course not correct, and therefore we overestimate in this case because of the fact that we should have, well, deducted this relatively high value over here, but we deducted only this small value over here. So that's the reason why ordinary squares overestimates the average treatment effect among the treated. Of course, it also overestimates the average treatment effect because of the fact that if theta is positive, well then actually we should realize that the average treatment effect among the treated is higher than the average treatment effect itself. And then finally late. Well, also in late we have to do some mathematics, but you can actually show that late is going to, well, be equal to another time 5/3 minus, well, in this case, theta over 6. So this actually implies that at the moment that theta is going to be positive, well then at that moment in time, late is going to underestimate the average treatment effect as well as the average treatment effect among the treated. Well, why is this the case? Well, this can be explained by the fact that we should realize that at the moment that we're going to look at S1 and S0, well, what are they? Well, they are actually defined over here, of course. What is S1? Well, S1 means that for a Z equal to 1, phi should be, well, what we should have had is that this thing should be larger than 0. Well, that means actually nothing else is that if this thing is going to be equal to 1, well, then actually V could be, well, any value larger than 0, then actually we're going to have that S is going to be equal to 1. Well, since we already know that V is always larger than 0, we should realize that actually S1 is always equal to 1. So in this case, we do not have any never takers because of the fact that you're either always an always taker or a complier, and never a never taker. And what is going to happen at the moment that we're going to look at S0? Well, for S0 we're going to see that actually, well, then we are going to have here minus half plus V. So in order to be having an S equal to 1, well, V should be larger than a half. We can say it in other words. In order to be a complier, which means of course that your S0 should be equal to 0, what we need to have is that V should be smaller than a half. So that implies that based on this, well, we can expect that given the fact that at the moment that theta is going to be positive, we have that V and U are going to be positively correlated to each other. That means, of course, that individuals who are going to be compliers, they have relatively low levels of phi because phi must be larger than a half. And that means, of course, that they will also have relatively low levels of U. Well, then based on this picture that we have over here, that means, of course, that compliers are actually over here. And what is late? Well, late is actually looking at the impact among the compliers. So that means that late actually looks at the average impact over here, whereas, well, the average treatment effect among the treated is actually equal to the average impact over here. So that's the reason why actually late in this particular situation is going to underestimate the average treatment effect among the treated. Well, that gives me the following simulation results, even though most of the times I've been talking now about positive thetas, what is going to happen in the case that theta is going to be positive. Let's first start in a situation in which theta is going to be equal to -1. This is a situation in which there is severe, say, negative correlation between U and V. And that's a situation in which, well, late is going to, in this case, actually overestimate the average treatment effect among the treated. as well as the average treatment effect, and ordinary squares underestimate. Well, these are the theoretical values that we have calculated, and these are the results. We do see that actually IV, well, does estimate quite well late. Well, maybe not so well in the case that n is equal to 100, but it does estimate quite well at the moment that n is equal to 1000. This actually shows that IV actually seems to, well, at least consistently estimate late as it actually should be. But it is not completely unbiased because of the fact that here we do see some kind of small, even though small, bias. With respect to ordinary squares, we see that ordinary squares at the moment that we estimated, well, it gives us actually the expected value of ordinary squares. That should of course be the case. Another thing that we immediately see is that IV generally is going to have a higher standard error than ordinary squares, as it actually should be. Then at the moment that we're going to go from theta equal to -1 to theta equal to -1/2, well, then in that particular situation we do see that things become less severe because of the fact that we see now that late and ordinary squares come closer at least to the average treatment effect among the treated, and actually also closer to the average treatment effect because of the fact that the average treatment effect is always equal to, well, 1.67. Now let's look at theta equal to 0. Well, theta equal to 0 means that there is no correlation between U and V, and that is a situation in which everything actually works perfect. That is to say that both late as well as ordinary squares are going to be exactly equal to the average treatment effect among the treated, and that is equal in this case to the average treatment effect. But we do see that both IV as well as ordinary squares actually also do estimate quite well not only their own, say, expected values, but also the average treatment effect among the treated. Again, we do see that in this case, obviously ordinary squares is better than IV because of the fact that ordinary squares does have a, say, much lower standard error than what we have with respect to IV. Well, then at the moment that we look at theta and half, then we get the opposite situation. Of course, then ordinary squares overestimates the average treatment effect among the treated, as I have explained in the pictures, and late is going to underestimate the average treatment effect among the treated. And again, we see that this actually is quite in line with what we find from our estimations. And finally, at the moment that theta is equal to 1, well, then we actually see that things, actually the differences become even more severe.